Hey everyone, this is just an example on absolute motion, and the question is, it states that this is a common quick draw mechanism with a slow cutting stroke attached to D, just here, and a rapid return stroke. If the driving crank OA, so this driving crank here, is turning at a constant rate, omega, or theta dot, so the time rate of change of this angle here, is 3 radians a second. Determine the velocity of point B below when theta equals 30 degrees. Okay. So the first thing we're going to do is attach a rotating axis to the bar BC. So if we have the bar BC, say this is just a bar BC. This is a really primitive drawing, but if this is BC, we attach a lowercase x, lowercase y axis to it. And we measure the relative position, or the radius, from C to, so say this is C, we measure the position from C to where where A is. So that position is going to change with respect to time because this is allowed to move within this slot, within that slot in there. Okay, so what we're going to do is we'll say the first radius is going to be a position vector from our origin. So that'll be, initially is going to be OA, but OA remains constant. So R1, R1 equals OA equals 100. So we're going to do this in terms of millimeters, okay? So that's 100 mil in there. $100 Okay, so the next thing we'll do is say that the radius R2 from the origin to C, so this length here is 300 mil. So if we use the law of cosines, we can find what this position is going to be with respect to any angle, because if we have a non-right angled triangle like so this is our OC here, this would be our OA here, and this is CA here. Now CA is going to be variable depending on what this angle in here is. Alright, so if we use the law of cosines, we can say that the radial length of CA is equal to the square root of R1 squared plus R2 squared minus 2 R1 R2 cosine of 90 plus theta. So if we go ahead and substitute these values in, we get square root of 100 mil squared plus 300 mil squared minus 2 times 100 times 300 cosine of 90 plus theta. So what we end up with is the square root of 100,000 minus 60,000 cosine of 90 plus theta. So if we differentiate our R term once with respect to theta, we have r dot, and we know that r dot is the time rate of change of position. Now time rate of position is going to be, let's move this out of the way. Our time rate of change of position is going to be r dot equals 30,000 theta dot sine of theta plus 90. And the reason this comes into play is because dr on dt, which equals r dot, is equal to dr on d theta times d theta on dt, which is that theta dot term there. So we're still missing a denominator. I'll put that in now. That's over the square root of 100,000 minus the 60,000 cosine 90 plus theta. 60,000, sorry. 90 plus theta. So this will be in brackets. 90 plus theta. Okay, so if we express that, this in terms of r, this becomes 30,000 theta dot, so we'll do it sine 90 plus theta dot on r. So for theta equals 30 degrees, we know that theta dot equals 3 radians a second, which was stated in the question. So theta equals 30 degrees, theta dot equals 3 radians a second. So we have that r equals the square root of 100,000 minus 60,000 cosine of 120, which equals, so let me plug that in the calculator. This will be in terms of millimeters, by the way. That's 360.555, which we'll just say is 361 millimeters. So 3 significant figures. Our time rate of change, r dot, is equal to, now it's convenient that we expressed our last term in terms of r, because we can substitute this value straight in and then find that 30,000 sine 90 plus theta, so that's sine of 120, times 3, which was our angular velocity or time rate of change of theta, over our r, which was 361 millimeters, is equal to, I'll just plug that in the calculator again, we get 216.173, which we'll just say is 216 millimeters. The 3 significant figures. Okay, so what I'm going to do is I'm going to answer the next part of this question in the next video. So I'll split this up into 2 sections. Thanks for watching, and it'll be covered in the next part of this video.